Beginning Log 5. This is Carson Isaiah Shen, head of the Mech Propulsion Systems Lab owned and operated by Aegis Mechatronics. This fifth log serves as a rough draft for the Peculiar Robot Contest, or PRC. The Fighting-Directed Laser Armament Mech, or Fidlar, previously obtained auxiliary subassemblies. The nanotronic fusion power core necessitates a secondary power source to facilitate initialization procedures and ensure operational stability. The long-awaited alphavoltaic battery modules have been received. This enables us to proceed with system-wide wiring integration and conduct initial power-up procedures to verify proper functionality of all installed components. Late-stage integration of the electrical systems is highly undesirable due to the complexity of the wiring layout. To ensure proper access and installation, complete disassembly is necessary to facilitate simultaneous internal access for all required wiring. Leveraging the current disassembled state of the mech, we can concurrently address improvements to specific sections before integrating the electrical system. Protective measures must be implemented for the protruding magnetic latches that lock onto the auxiliary arms. To accommodate the thermal dissipation requirements, the current design necessitates the incorporation of additional ventilation channels. The implementation of selective armor plating will be prioritized to safeguard critical front-facing components. However, simple modifications will be necessary before installation. Unnecessary markings and extraneous lettering pose a potential risk for misidentification and subsequent misapplication of components. Therefore, such markings are removed and the affected surfaces undergo refinishing to ensure clarity and proper component utilization. This process is to be followed for all subsequent iterations of the design involving selective armor plate additions. The folded auxiliary arms will enhance projectile deflection while offering a secure, close-fitting configuration against the newly installed supplemental armor. The missile array incorporates similar armor enhancements that will further protect the engine assembly underneath. A thin weld bead prevents armor from being attached flush to the missile housing, but it is easily removed. In-house development of a specialized grinding tool is required for efficient removal of markings from the smallest armor components. These strategically placed plates provide targeted protection for critical engine components. After the last recording was publicly released, we received an inquiry concerning the calibration of the nanotronic fusion core, where an incorrect sinusoidal wave could cause harmonic stabilizers in the oscillation matrix to become dysregulated. This was already addressed, but will be recapped here for anyone who shares the concern. A recalibration was performed to confirm potential inefficiencies. The core has optimized its neutron flux channeling algorithms, which will lead to a 2.7% increase in overall energy output and a 14% improvement in core stability. If these assurances are insufficient, we can initiate a remote core diagnostic override at a future time. The electrical systems will be addressed after one last component is completed. Although the LIDAR scanner excels at producing high-fidelity, short-range images of the nearby environment, it will not be able to adequately detect long-range threats, which will hamper the full potential of the laser cannon and missile array. While not providing the same level of detail, a radar dish excels at tracking the movement and location of specific targets over a wider range. Certain radar frequencies can penetrate smoke, dust storms, and even some cover, allowing the mech to detect hidden enemies or maintain situational awareness in obscured environments. The radar dish possesses dual functionality, enabling long-range communication reception from central command for coordinated battlefield operations. After connecting the waveguide and duplexer, the antenna is also ready to be connected to the pending electrical system. Speaking of which, initial installation of the electrical systems begins with solenoid switch integration. Robust, high-current solenoid switches were selected for their availability and reliably fast remote operation for high-power electrical systems. After marking the location of mounting pins, holes were cut through the LIDAR housing with a precision plasma arc cutter. Before mounting the switch array to the sensor housing, electrical wires need to be integrated and routed through the armor plating. As mentioned a few logs prior, Aegis Mechatronics does not usually work with high-energy weapon systems. However, we do have plenty of experience with electrical engineering, so connecting standard components is not difficult for the lab team. Lucky for us, the alphavoltaic battery modules still have plenty of room for mounting within the Fidlar housing. It was completely unnecessary to use magnetic mounts here, but they will still make removing and servicing the alphavoltaic batteries a little bit easier. After integrating the solenoid switch into the alphavoltaic battery rails, power cables were routed through the bottom of the upper shell in order to reach the primary laser cannon. Electrical interfaces were implemented using connectors on each major subsystem to facilitate modularity and independent operation. A photonic emitter was welded into the lower housing, which will help to energize formation of laser beams within the collimator assembly of the upper housing. An oversized cable nests inside of the upper housing of the laser cannon easily, but can be extended to simplify attachment of the lower housing electronics. A quick test found a short circuit somewhere within the system. Additional probing found that the first connector installed for the solenoid switches was crimped incorrectly, leaving exposed pins that touched each other. Failure to integrate additional photonic emitters led to a full rebuild of the internals. Wires were upgraded to flexible silicon insulation, and a proper circuit board was chosen for scratch-building power rails. After soldering in each pin, They are simply bent into each other to form a continuous parallel circuit. The use of a proper circuit board significantly simplifies the addition of more electrical components. The last subassembly to integrate into the electrical system is the plasma turret, which requires additional mechanical work. As always, ventilation is important for these high-energy weapons, so the housing was rebuilt to include adequate cooling. Another heavy-duty cable identical to the laser cannon input was installed on the secondary turret side. Functional verification of all photonic emitters has been completed. Additionally, a dedicated maintenance connector has been integrated for the plasma turret. Final assembly includes the installation of the radar dish into the sensor array. Afterwards, it's a simple matter of re-establishing a connection between all electrical connectors and reassembling the components as shown in previous logs. Repetitive Fidlar disassembly and reassembly have yielded a comprehensive understanding of optimal component handling procedures. Remaining bits installation on the mech will prioritize minimizing disassembly. However, painting will necessitate a complete disassembly. We'll be open to addressing questions or concerns on behalf of Aegis Mechatronics. Attached is test footage of the electrical system in use. Feel free to leave your comments before the final audit is submitted later in the year. We're almost done with the build, but there's more to come. That's all for now. Thank you to our benefactors for continued support. This is the end of Log 5.